Okay, so this is chapter 17 on rigid body dynamics. Okay, so before we can do dynamics, I need to define what is known as center of mass and moment of inertia. Center of mass is the location where you can assume the entire mass of the object is located. You can assume where the mass of the whole object is located. So think of you can think of the body consisting of multiple submasses. Like, for example, for a person, it's like there are two hands, each of them have mass, legs have mass, but where exactly is the weighted sum of the mass? That would be somewhere close for humans, actually close to your stomach, and the formula for that is x bar and y bar, which is the weighted sum of the locations of the center of mass of individual objects. So this will become clear when I solve the problem. Moment of inertia is just like mass. Mass is defined as the resistance to movement. So bigger the mass, the higher the force you need to apply to a body to make it move. For inertia, it is the resistance to rotation. So bigger the inertia, it's harder to get a system to rotate. The formula for inertia is, well, inertia is always, as I said, resistance to rotation. So it's always about an axis. So in this case, the body is rotating about, let's call that the z-axis. So I'll write Iz as integral r squared dm, where r is the distance of the point mass dm from the axis of rotation, and you need to do that integral over the entire object. Now, a first course in calculus will actually teach you how to do that integral. It basically boils down to either a double integral for a planar body or a triple integral. I'm not expecting you to know how to find a double or triple integral in this course. What we'll do is, I will give you the inertias for different objects. So the inertia is a property of the axis of rotation. So different axes would have different inertias, and also the geometry of the object. Okay, so all these 8 cases are some common geometry. Then all of these assume that the mass distribution is uniform. Okay, so the most important ones, and you're not expected to remember the formulas for any of these because I will actually give that to you in the problem. Okay, so let's look at one of them carefully. Let's say look at the cylinder. Okay, so a cylinder or any object in 3 dimensions has 3 axes, x, y, and z as shown. This table gives inertia about all 3 axes, I, z, z, I, y, y, I, x, which means that if that object, the cylinder, rotates about the vertical axis this way, then usually we use this inertia. If, however, it rotates about the y-axis like this, then you use that formula. Okay, so you need to figure out what axis the object rotates, and then use that formula to do the problem. Just don't go by x, y, and z. Let's look at something else. So the cylinder is a common geometry which will feature in many of the problems. A disk is also a common one. Okay, so inertia about z-axis is that as if the disk is rolling, but if you spin the disk about the other axis, y or z, the inertia is different. You see that I, z is half. Inertia about x and y is 1/4, which means that inertia about our x and y axis is 1/2 this one. So it's easier to rotate a disk about the y and z x-axis versus the force will be required to rotate about the z-axis. Okay, that's an important geometry. A thin ring is important, and a slender rod is important. Again, you do not have to remember. Most of the time, we will always give you the formula. Don't remember those formulas. Okay, so that comes from that integral I talked about. You're not expected to know that. A few more things before we get started. There is a theorem called parallel axis theorem, which we'll use quite a few times in this course. Parallel axis theorem. Okay, G is the center of mass, and let's say we know the inertia about the center of mass, so let's call that IG. Okay, by the way, all these inertias in this table are about the center of mass. You can see this G. That's where the center of mass is located. For uniform geometry, the center of mass for an object like this, which is symmetric, is going to be at its center, at its geometric center. Okay, so G is something which you got to remember. It's the center of mass of the object. So what does parallel axis theorem give you? Well, if you know the inertia about G, which is an axis passing through the center of mass, then you can find the inertia about a different axis parallel to the original axis, but at a distance of d. Let's call this distance d. Okay, and we need to find the inertia about this axis. So let's call this as zg and zo. So if you want to find inertia about O, which is parallel to axis zg, then the formula is the inertia about g, which by the way I'll provide you, it comes from the table, plus the mass of the object times the distance, the perpendicular distance from zg and zo. So that is the formula you have to know. The final thing is called, well, you got to know, is radius of gyration. So radius of gyration is basically if you take any geometry and collapse the inertia to a thin ring, which has an inertia of half mr square, then the inertia can be represented using this formula. Okay? K is the radius of gyration. So what is done here, what it really means is, assume we have a geometry like so. you try to approximate this as a thin ring. Okay, you find an equivalent K so that the inertia about so that's the geometry. It's a cylinder. What we try to do is we try to find a ring of radius K such that the inertia of G equals the inertia of the ring.
So solid?
It's a ring, so it's like this. It's not a disk. A disk is fully solid. And so when you collapse it into a ring, so the inertia remains the same, but what is the radius K so that you can actually map the two inertias? And that's just a way in which you can make your life easy, because if you give K now, you can start comparing different geometries, right? So if I give you a disk, sorry, a cylinder rod, I give you a disk, and then ask you, can you compare the two, the inertia of the two? And there is really no way to do that, because inertia for disk is very different from inertia of a cylinder rod. But if you collapse that to a ring, that is, you collapse this to a ring, the rod to a ring, you get a K. If you collapse the disk to a ring, get a K. And now if you compare the Ks, you can make sense which of them, you get a sense of how the inertias are different.
So does K represent like the inner radius?
The thickness is so small that you can ignore the thickness of the ring.
But K is like the inner radius of the ring, or?
It's the radius of the ring. The thickness is ignored. It's the radius of the ring. So one way we would give you inertia is, well, we would give you the dimensions of the object. So for example, for a disk, for a cylinder rod, it's mass times length squared divided by 12. That's the inertia of a cylinder rod. The other way we could give you the inertia is we could just give you K, in which case you're supposed to use that formula, mk squared, to figure out the inertia. Okay, it'll be clear when I solve problems. Okay, any questions on this? So today we're going to just learn how to find the center of mass and how to find moment of inertia for different geometries. So determine the moment of inertia about an axis perpendicular to the page and passing through the pin O. The thin plate has a hole at its center. Its thickness is 50 millimeters. So the thickness is the thickness which you cannot see. It's basically inside the plane. And the material has a density of 50 kg per meter cube. Okay, so what the problem asks you to find is inertia about axis passing through the page, which means that the cylinder, the disc, sorry, the plate is moving about that axis. So you need to find inertia about this axis. Okay, now, well, first thing you do is ask yourself, do you have a table which provides the inertia for that geometry? So you can go back to the table I showed, which is right here. And you see that none of those cases involves a plate with a hole. So you cannot use the table to find inertia. But what you do know is, you know the inertia of a thin plate, and you know the inertia of a disk. And the way to think of a plate with a hole is, it's basically a plate with the hole cut out. So if I can find the inertia of the plate, and then find the inertia of the hole, then I can just subtract the two and find the inertia of the plate with the hole. That's the approach. So what we'll do is, so here's the plate with the hole. The lines indicate which part is not hollow. So we're going to try to find the inertia about O for the thin plate without a hole about axis O, and then subtract out the inertia of the hole or a disk about the axis O. In other words, I'm trying to find the inertia about O for a composite object, I'll call them 1 and 2, which is the inertia of the plate about axis O, that's why the IO. 1 denotes the plate, the rectangular plate, minus inertia of the disk about O. 2 denotes the object, which is the circular hole. Okay, so this is the unknown, and we're going to find this and this, the right sides, to figure out inertia. Okay, so let's find the inertia of the thin plate about axis O. Okay. So the table which I showed you has inertia about axis G, which is the center of the plate. Okay, so let's go back to the table. We're looking at a thin plate. Okay, which of those three I's should I use? There's IZZ, there's IX, IXX, IYY. All of those indicate inertia about G, but different axes. I need to use IZZ, right? Because if I can find inertia about Z, then I can find inertia about a different point. In this case, it's going to be this axis. So O is going to be this point because the disk spins about the axis O. So I'll use IZZ, which is 1/12 mass times the length of the side squared and summed. So that would be 1/12 the mass, which is going to be density times the length, width, and thickness, which is 50 millimeters, so 0.05. So A square plus B square, A and B are the lengths. 1.4 square plus 1.4 square. So this is the inertia about G. If you want, you can call it G1. Right? The table only gives me inertia about G. But I need to find the inertia about O, which is separated from G by a distance equal to this. This is D. That distance is, so that distance is going to be, the diagonal of a square plate is, well, it's going to be 1.4. It's going to be 1.4 square root of 2. That's because I need to do Pythagoras Theorem to find the diagonal. Right? I know the sides 1.4, 1.4, so I do 1.4 square plus 1.4 square. I got 1.4 square root 2, and this length is half of that, so 0.7 square root of 2. So plus 1 mass times the, well, density times the length, width and breadth times thickness times the distance from G to O, which is 0.7 times square root 2 square. Okay, so this, if you do the math, it comes out to be 6.4 kg meter square. Okay, so that takes care of the plate. Let's go to the disk. I02 equals, so inertia of the disk. Again, the table will only provide inertia about G, the center. So we have to go back to the table and find inertia for the disk about G. So which of those inertias would I use? This Ixx, Iyy, Izz. We can ignore this one. You don't want that. Which one should I use? Ixx. How is the circular disk is planar? If we want to find inertia about the axis passing through G oriented that way, right? So it has to be Izz. It's not Ixx because it's not rotating this way, it's going to rotate that way. So Izz is half mr square, half times mass. Now what we're doing here is we're trying to find the inertia of the disk as if there was no hole, it was actually a disk. So we need to find the mass, the density is going to be same as that of the plate, so 50 times the area of the disk, so that's going to be pi r square, so pi times radius is 0.15 square times the thickness, which is 0.05, so that's the mass, times the radius squared, so 0.15 is the radius squared. But that's the inertia about G, about the center, G2. We need to find the inertia about O, so that's going to be, by the parallel axis theorem, it's going to be the mass, which is 50 times pi 0.5 square times 0.05, that's the mass, times the distance from O to G, which is same as before, 0.7 square root 2. So this comes from parallel axis theorem. Okay, so everything there can be computed because we know the values of everything. So 0.175 is the inertia about 2. So the final step is to find inertia of the composite object consisting of the plate with a hole. So that's going to be 6.4 minus 0.175, and the answer is 6.23 kg meter square. Okay, any questions? So this is, yeah, question.
Why didn't we use the Z prime?
Sure. So the question is, well, we know the inertia about Z prime. Okay, can we use the inertia about Z prime? Well, you could potentially use the inertia about Z prime, in which case it will be the point A is somewhere here. It's not over here. Sorry, the point O is not there. It's over here. So you can use 3 by 2 mr square plus mass times the distance from. Let me go to the figure and tell you. So the question was, can you use the inertia about Z prime, which is the inertia about this point? Yes, you can, but then you'll have to use this distance for the parallel axis theorem. You'll get the same answer. I normally recommend don't try to use IG. Sometimes the question can be tricky, and you will try to do something and you get the wrong answer. Always go by IG plus md square. But in this particular case, if you use inertia about this point, which is given in the table, it should be perfectly fine. It should give you the same answer. Now, this is not the only way to solve the problem. There's another way to solve it. It just matter on how you compute the inertias. So another way, and I just laid down the steps, but you should try to check it yourself. Another way is to first take this composite object and then find the inertia about G. So I find IG 1, 2 equals Ig1 minus Ig2, where G2 is the center of this one, G1 is the center of the plate. So that's step 1. You first find Ig of the composite structure, the left one. Once you do that, the second step is, in order to find the inertia of the composite structure about O, which is IO1, 2, you can take Ig1, 2, which you already found, and then do the mass of the composite section should involve the whole too. So write like this, times the distance, this is the distance squared. So the second method is a little bit, it just involves 2 steps. But you can go and check doing it this way, 2 parts. First, I found the inertia about G for the composite structure, and then I found inertia about O using parallel axis. So this one involves using the table first, and then using the parallel axis theorem. But in that first part, what I did was I used the parallel axis theorem each time. So don't do it both ways. You just choose one way you're comfortable with and solve it using that way. Any questions? Okay, so let's see if we can solve this problem. Determine the moment of inertia Iy for the slender rod. The density is rho, cross-section area is A. Express the result in terms of mass m. Okay, so you asked to find Iy. Okay, I need to give you inertia about G. So when you're looking at the table, you need to find inertia about this axis. So Ig, let's go to the table and try to find the inertia about axis G, but parallel to Y. So go to the table. Slender rod is right here. So X, Y, Z. Which of those axes corresponds to the one we are interested in? X, Y, and Z. X is fine. Actually, Y is also fine. They are the same inertia. It's not Z because Z denotes rotation about this axis. But X and Y denote rotation about that axis. That's what we're interested in. So Iy is 112 ml squared. So Ig about the y-axis is 1 by 12 ml square. Okay, so to get a numeric value, what I would recommend is just use m equals 1 and length equals 1. You can ignore the rho and a. So pole I, y, y. It should be fairly easy to do. You have to use a parallel axis theorem. It's open. Yeah. The pole's open. Right? Yeah, it's open. Yes. I'll stop in 30 seconds. Fairly easy. Stop in 30 seconds. Yeah, I'm stopping poles. Okay, so IYY is IG about the axis YY plus the mass times the length or the distance from axis Y to the center. So that's going to be L divided by 2, half, right? ML. So this is mass times length squared divided by 12 plus mass times length squared divided by 4. And so if you do the math on that, it comes out to be ml squared divided by 3. So if you put m equals 1, L equals 1. You should get 0.33 kg meter squared. Okay, 0.3, 0.33. Missing something?